Hello. Today I want to talk to you about dialectical categories for friends. And by friends, I mean anyone who actually likes category theory. I want to talk only about 10 slides, and I want to make this an experiment in kind of mathematics communication. Because normally I kind of talk mostly about the motivation for doing something, some piece of work, and about what I want to get out of this piece of work. But today I wanted to just kind of describe the piece of work as abstractly as possible, because I want to see what other people kind of can make out of it and what they want to make out of it. So I have only 10 slides, and I hope this will work in less than half an hour. Let me see if I can share the screen by myself. There. I'll have to check later on if I can see the slides properly, but I will try to kind of enter full screen. So by now you should be seeing that I only have 10 slides, excluding this one. And that is something that I was trying to do in February. Now we're in June, and I'm still trying to do it. So what do I want to cover? I want to cover my thesis, which I finished writing in 1988 and submitted and defended in 1989, and only kind of got the degree granted in 1990. And only in 1991, I got the technical report made out of it. And this thesis is very short, only has 88 pages, and it has 4 chapters and 4 main theorems. All of those theorems are the shape X is a category that's a model for a logic Y. And I know that some of the friends that I intend this video for are not very fond of categorical logic, and in particular, they're not very fond of logic altogether. So they will have to trust me that theorems of this shape, X a category that's a categorical model for a Y logic, are important theorems. So we start as usual from a Cartesian closed category C, and it has coproducts, and the coproducts are slightly special. That's the ellipsis, the 3 dots over there, but you could think simply of sets. And our 4 theorems are kind of, and I want you to kind of see them all so that we can kind of, so that you know how far we get into this. So the first theorem is that it's the first original dialectical category, and this is a model of intuitionistic linear logic without without the modality bang or shriek, or whatever you want to call it. I call it modality instead of exponentials, because the expression exponentials, that is the one that Girard uses in category theory, tends to mean something completely different, and I kind of want to use it in the category theory meaning here, so I call it the modality bang. The second theorem is exactly that. The category that I'm going to describe, which sometimes I call DC and sometimes I call Jidaio, that this category plus a monoidal comonad is a model of intuitionistic linear logic with those modalities. One thing that's fairly special about this model is that this monoidal comonad bang is a co-free comonad. And I'm going to get to that in a minute, but that is very different. The third theorem was a suggestion of Girard, and it simplifies the original category DC or Jidaio, and it's a model of what Girard was more interested in, which is the full classical linear logic, which I'm writing as CLL. And the fourth theorem, it's similar to theorem 2. So it says that this category GC has a fairly complicated monoidal comonad, but this is a model of classical linear logic, but it's also a model of full intuitionistic linear logic, which is another complication that you may or may not want to think about. I kind of started trying to, even if I say that logic is not the main thing for some of my friends that I want to listen to this video, it's still kind of important to say a little bit about how do we do categorical models. And as I'm saying, the challenges of modeling linear logic, at least the challenge as they were in the late 80s, is that traditionally categorical logic in the shape of Liouville theories and kind of even the models of polymorphism that happened in the early 90s and stuff like that, and models of realizability and all this stuff like that, they tend to be, the traditional model tends to be about using real products and using as the adjoint to the real products sets of functions, all functions from A to B, all functions in the category that we're dealing with in this appropriate category. So this is what happens in intuitionistic logic, and it is the main canonical model of doing categorical logic. So whenever you have, and when I say real products, I don't mean real in the sense of the real numbers, I mean kind of categorical products, Cartesian products, products that satisfy the traditional limit conditions. So they are real limits, and they have projections and diagonals. Now, when we are actually using this morphisms in the category, the diagonals and the projections, to interpret the logical system that we're dealing with, they will correspond to duplication of resources being the formulas of our logical system, and to deletion, the projection, the deletion of some formula. So this is not linear, and we needed to use tensor products and internal Holmes in category theory. And as I said, in the late 80s, this was very different, and people got a little bit frightened by that. But nowadays, everyone kind of likes monoidal categories better than Cartesian categories, so we are in a much better situation. In any case, if you were wanting to model something like linear logic, the hard bit was always how to define the Bang operator. And the Bang operator is what makes linear logic a better logical system than the other linear-like systems that we had before, because the Bang operator makes everything usual for, again, so you can have your cake and eat it. You can have a logical system that pays attention to where resources are being used, but at the same time, you can say, okay, today I'm not paying attention to this business of linearity. I just want to be traditional, and I'll kind of just have my intuitionistic logic. So let's kind of go for, so we have 4 constructions and 4 theorems. So let's kind of start in earnest thinking about the first category. Here I'm calling Jidaio, but in other places in these slides I'm calling GC. The difference is just that C, as I was saying early on, can be sets, and you might as well think of them as sets, but it could be any category C with Cartesian closed with co-products. So the objects of this new construction that we are going to be doing over C, so the objects of this DC are triples. They consist of 2 objects of C and a relation between these 2 objects. So alpha, so the objects are triples, U, X, and alpha. And sometimes I call the whole triple A. because it's easier to have a single name for the object. And then the relation is a sub-object of u cross x. And what makes this setting special, it's not the objects, of course, but the morphisms. And the morphisms here, I kind of drew them by hand in my whiteboard because I like to have them with arrows showing who's the domain and who's the codomain. So morphisms of DC are pairs, a little f and a capital F. And the little f goes from u to v when we have objects ux alpha and v and another object b, which is v y beta. And the difficult thing is that the second component of the morphisms is this capital F morphism that goes from u cross y back into x. And it's not any old pair of maps, little f and capital F. They have to take the relation alpha to the relation beta. And how we do that? Well, we have more than one way of doing it. But the original way was saying, oh, okay, you take your alpha, as you see in the second picture, which is a subset. Now talking sets to make my life easier and your life easier. So alpha is a subset of u cross x. So the pairs of little u's and little x that are related by alpha. I take the pullback of this alpha along the map that just takes u cross y, does the projection on the first coordinate, and then does the f on the second coordinate. So this little square here shows that this is a pullback. I do a similar thing for the beta, that is a subset of v cross y. But in this case, I just use the function little f and the identity in y, get another pullback. And these are pullbacks, the pullbacks kind of give you a sub-objects of u cross y, and there is an order on the sub-objects, so you know that there is a unique filling function, which is the one that I'm drawing as the little dots there, as we normally do. So, you'll say to yourself, well, okay, it's not the easiest construction ever, but not the hardest one either. Triples are easy. The two first components of the triple are just sets, and the third component is a relation, which is also easy. But what is kind of surprising and interesting is how these triples transform into other triples. And this is through this pairs of morphisms that have this somewhat dual, self-dual kind of, in a way, characteristic. And then the first theorem tells, which I presented in Boulder in 1987, is that the category DC has a symmetric monoidal closed structure and products and weakable products, and that makes it a model of intuitionistic linear logic without what Girard calls exponentials. So without the bang, which I said I was going to call a modality, but I just forgotten because I just copied it from previous talks. And to show this theorem that I presented in Boulder in 87, you have to show that DC is a category, because the morphisms being complicated, you have to prove that they compose the way you expect them to compose, that you have identities which are going to be clearly just identity in the left coordinate and a projection in the right coordinate. You have to show that there is a tensor product, which is fairly obvious in this case, because you just do Cartesian products in each coordinate and then kind of see what and then see that the relation can be used as a Cartesian product of relations too. And the interesting bit comes when you actually take this complicated notion of morphisms that we're discussing here, and you actually kind of internalize them to make that an internal home in your category. So good that I kind of came back, because I forgotten to mention that this condition on the pullbacks that we went over carefully, thinking of the second diagram, can be seen as simply saying that for all little u's in u, and for all little y's in capital Y, if u alphas f of u and y, then f of u betas y. And this is the same thing as the condition on the pullbacks that I described before. And you kind of have to kind of get used to the idea that you can read this big fat arrow here as either thinking that u alphas f of u y is smaller than f of u beta y, if you're thinking of relations as being things that have maps that have the target 0, 1. So either a pair is related 1 or a pair is not related 0. But you can always think about this big fat arrow as being an implication. And if it's an implication, then it can be an intuitionistic implication or a classical implication. And I will prefer to think of that always as an intuitionistic implication. So when you manage to internalize the function spaces and manage to show that they work, you still have to think about real products, and they are easy. You just kind of take a product on the left coordinate and a co-product in the right coordinate, and then you show that this whole thing works, and that that you do get a symmetric monoidal closed structure. And I kind of love to do this proof that that's a symmetric monoidal closed structure, because it just shows how things fall into place the way they should, which showing how each bit can be used the way we want to use it. And I particularly like the fact that this was something that I had written just by hand for myself when I went to Boulder, and in a night before the conference started, I was talking about to people over a glass of wine, and I said, well, that's what I did. That's what I'm doing. I'm trying to show this, and I did this part. And I kind of talked to Robert Seeley, who said, oh, no, you didn't. And I said, well, no, yes, I did. I have. And he said, no, you didn't, because I've tried so hard to do it, and it can't be done. And I said, no, okay, I'll go. I went to the room and collect my notes, and showed it to him. And the next morning, instead of being cross or anything like that, he kind of came to me and said, I think what you have to say is more interesting than what I have to say. Why don't you give a talk in my place? Because the program was filled. So, it's been a very nice interaction altogether. Now, what I was kind of discussing with Robert at that stage was exactly this second main theorem, which is this idea that modeling this modality that makes the whole logic become like the logic that we're used to, again, is hard. And this is hard because you need an operation on objects, or which we're thinking of as propositions of the logic, such that for these objects that have this mark, this exclamation mark on them, you can do duplication, you can do erasing, which we will think of as being a mapping into the unity of the monoidal structure. You can do something that later on Phil Wadley started calling dereliction, which is saying, well, if this proposition here is something for which I can duplicate and erase things, then proving one of those non-linear propositions implies having a proof of the proposition itself. So that's the relation pling A goes to A. And more complicated still, you need to do this. It's not that you need to, but it's one of the things where that will give you some mapping which goes from pling A to pling A, which again Wadler calls jigging. And this kind of modeling, if you are a category theorist, you don't want an operation, any odd operation on your propositions. You want things that are at least functorial, that at least preserve the kind of composition that you had amongst your propositions before. So you want something that takes up a mapping between A and B and gets you a pling of the mapping between pling A and pling B. And the difficult thing is to show that that this functor pling is to discover which properties you should ask of this pling functor so that it will really model modalities in the linear logic and recover from that the properties of normal intuitionistic logic. And in this case, the definition for the modality, which was a suggestion of Martin Hyland, was actually easy, because he said, well, let's kind of try to think about the free monoids on X, because we then get for each object that we're dealing with, we get a set U, and we get a finite sequence or commutative sequence of axes. And we're going to try to think of these axes as being counterexamples to the theorem that we are proving. So he had other standing in place intuitions for that, but the calculations worked really well, which was slightly different from the chapter 1, where he had said that the calculations should give us a Cartesian closed category. And being a young PhD student, I worked really hard to try to prove that they were a Cartesian closed category. And at some stage, I got fairly desperate, and I came and said, I'm sorry, this is not a Cartesian closed category. This thing is not a real product. I cannot prove that it's a real product. And instead of being cross and saying this woman cannot do the basics of category theory, he looked and said, oh, that's interesting. That reminds me of something that I've heard recently, and that was linear logic. So kind of being a supervisor is a hard job. As I was saying, the pling side is what is not obvious. It's what caused lots of the difficulties that we had with the modeling of linear logic. And this first example that I particularly tried to cope with, it was actually end up being very easy, because we end up in a mathematically much more kind of good situation than lots of other people later on. And that's because, proving that the pling that I described to you a minute ago, the one that takes U to U, UX alpha to UX star alpha star, where X star is the commutative monoid in X, and alpha star is just repeating the alpha relation to in each one of the elements of the sequence x1 to xk. So this so-called free commutative monoid in C is actually a very well-behaved object in category theory, and hence the pling will get was one we calculated gave us a monoidal comonad. And even with these natural transformations that transform product of comonoids into a comonoid of the tensor, and this worked. So this, for people who don't know, this M and MI are the so-called Sealy isomorphisms, and you know, the other direction is trivial, but this direction you have to ask for them. And so that's what I actually proved, was that they were there, and that it make the whole comonoid thing, comonad and comonoid thing work. But, you know, as I keep tripping over comonad and comonoid, just because they are really intimately related, and having the comonad in the category kind of induces comonoid structures on each one of the objects. And there are several propositions that you have to prove to show the theorem at the bottom of the screen. And what you take to be the given and what you actually prove is up for discussion, and there's been lots of discussion about it. But in any case, you always want, that objects of the shape pling A have a commutative comonoid structure, because you want to be able to duplicate them and delete things from, delete it, and kind of, when you duplicate them, you want them to carry on having the good properties of duplication. And you want the whole set of those objects to behave in a sensible way. So as I was saying here, you want the comonoid and the coalgebra structures, because whenever you have a comonad, you end up having Eilenberg-Moore coalgebras and co-Kleisli categories. So you want the comonoid and coalgebra structures to interact in a nice way. So I think that nowadays the easiest way to say that is the way I'm phrasing it down here, which is to say that there is a monoidal adjunction between the category that we started from and its co-Kleisli category for the monoidal comonoid above. And the fact that it's co-free is the extra cherry on the top of the cake, and doesn't happen for most of this of the models of linear logic, but it happens for this one. So I kind of needed to make a historical note that I actually started talking about a minute ago, which is that when you're thinking about relations in categorical setups, there's more than one way of thinking of them, right? You know, you can think about a relation as being a subject of a pair of objects, as I did in the first picture that I showed you. Or you can think about a relation as being maps into, say, true, as I also mentioned, true because 0 is false and 1 is true. So either the relation holds or does not hold. And the kinds of generalizations that you can do for these two different ways of thinking of relations will give you different stuff. And I just wanted to know that, and if we are kind of thinking of discussing possible generalizations and applications, you can think of the two different versions as perhaps generalizing into different directions. And I actually kind of discussed quite a bit of doing the second version, the version that goes into true, quite a bit in this paper called True and Dial Cousins, because lots of people like much more the true construction than the dialectica, and I feel offended by that. So the third main theorem, as I said, there are only 4, and we have to get going because we only have 30 minutes. So the third main theorem is this thing that I'm writing over here. We want to simplify the original dialectical construction if linear logic is the goal. And that was a great suggestion of Jean-Yves Girard, to whom I'm very, very thankful. And what he said is, well, why are you taking this extra detour into using the first object to map back? Why don't you just take maps that go down in one component and up without this dependence on the first coordinate. And you're going to, and he said, and it's going to be very nice. It's going to be much nicer for modeling classical linear logic, where he was right. It was, and he also said it would be good because you could think of it as being a different logical phenomenon, which this one hasn't worked out yet, but we keep thinking of how to do that, and we kind of get to that in a minute. So if you do that, if you kind of take this simplified morphisms, which lots of people like better because they're more similar to choose space construction, you kind of get a category which I used to call GC, but nowadays I tend to call Dialectica true sets, which has a symmetric monoid closed structure and products and co-products, and hence it's a model of a classical linear logic or something called full intuitionistic linear logic, which again, at some stage, I'm going to pester you with, but not today. But that is, as I was kind of writing early on, without modalities, or I think I wrote before, bang free, but, which is not a very good notation because free in this case is being used in two very different meanings. One is without something, which is the meaning that I had before, but the other one is free in the sense of free objects in category theory, which are the things that are just initial objects in some other category. So, as I said, Girard says that this category should be related to Henkin quantifiers, and despite all the interesting work that has come after that, we haven't been able to make, I have not been able to make this this relation to Henkin quantifiers an interesting theorem. It's one of the things that's still on the to-do list. And the fourth main theorem was really the hardest one to come by. And that's the one where I actually have to thank Chieko Kan for his helping hand. Because Girard, when he suggested this category, which has the objects very similar to the ones in the original Dialectica, but just going backwards, and so the F here doesn't have the dependence on U, it simply goes from Y to X, and satisfies the same sort of dialectical condition on the relations, but simplified. So when Girard suggested that, he said, well, you're going to have a very obvious way to model the pling in this case, and or the bang in this case, and his suggestion was simply to take this monad pling to the U, which is a monad in C that induces hence that will induce a comonad in the dialectical category GC. And I tried and I tried and I tried, and this thing did not work because you could prove that it was a comonad, and you could prove that you had coalgebras and all the stuff that we like for categorical reasons, but you couldn't do the duplication and the dereliction that the dereliction you couldn't do the duplication and the erasing of prepositions, which I needed to do. I needed the free monoid on X to do. And I was kind of talking to Thierry about that, and I said, well, look, this is annoying, isn't it? The bang operator is supposed to do two different things, something about the comonad and something about the comonoid structure. And I either can do one or the other, depending on the comonad that I use, but I can't do both. And he looked at me and said, well, why don't you compose them? And, if you have kind of learned category theory traditionally, one of the first things that you hear is that monads and comonads don't normally compose. That actually you need to have a distributive law between them, so that, I mean, it's not that you have to, sometimes they compose, but normally when they compose it's because you have a distributive law between them. And in this case, I was fine because there was a distributive law between these two comonads and also between the two monads in C, and everything worked. So I have a comonad bank in GC that's the composite of the two comonads that I had before, and that gives me a monoidal adjunction between GC and its Coke-Lisle category for this composite comonad. And it's not free, but who cares? You know, freeness is overrated. So now I wanted to talk a little bit about applications and generalizations, because, you know, you might be asking, you know, you didn't want to talk to me much about motivations, but where are we going to take this? And I'm trying to take this into several different places. So as part of the ACT Adjoint School into 2020, we have a new preprint, which is work of Elena de Lavore and Wilma Leal, or Wilma Leal, or Leo, perhaps, do not know how, I mean, it's a Spanish name, so it should sound more like the Portuguese, where we are kind of using these ideas of dialectical constructions to model pattern nets for chemistry and biology. And they are very excited about the application, and so am I. With some young guys from Italy, we are taking it into a completely different direction, where we make the logical system that we are modeling more complicated, and we start having I mean, the systems that we've been modeling so far here are propositional systems of linear or intuitionistic logic. With the work of Davide Trotta and Matteo Spadato, we actually taking it to model systems with quantifiers. And there we have another preprint called the Gödel vibration, which we hope will be accepted somewhere soon. With Samuel Gomes da Silva, who is a set theorist in Brazil, we have a collection of interesting work on applications of this setting to set theory. And here, the thing that, I mean, the person who made the initial connection was Andreas Blas, who noticed that the categories that I was talking about when modeling linear logic were the same categories that someone called Peter Voces, a Czech set theorist, was using to show cardinalities of the continuum being related. And I talked a little bit about that in the Finding Right Abstractions workshop. And the most interesting thing is that we want to kind of find the relationship between these ideas of these mathematical ideas of dialectical constructions with the constructions that David Spivak kind of likes so much, which he calls the poly category, and with notions of lenses that lots of people have been describing, and because of the fact that people have very different intuitions about them, they are kind of difficult to pin down very, very precisely. And if this relationship with poly and lenses kind of gets sorted out, then maybe we can also sort out some relationship with differential linear logic, but that's just kind of wishful thinking at the moment. Some things that are not wishful thinking but haven't been done yet are multi-agent systems based on linear logic and dialectica categories, and a whole collection of game models that we have known about ever since, and was an EPSERC project for me kind of many years ago. And the idea there is basically that that each one of those objects in a dialectical construction is like a superpower game, where instead of playing the game like a good person, you just say, well, my strategy is this. And the other person just says, and my strategy is that. And we just kind of check using the relation which one is better. And this superpower games should be relatable, we hope, to more traditional games. So this is another application that I want to develop at some stage. And, you know, if you want, and there's loads more of work using Dialectica that I don't have the time or the ability to discuss right now. And some of it I understand and some I don't understand. But you can read about the stuff that I know that exists in this GitHub list with links to papers. And I think that's it. I hope having everything set up in this very short video kind of helps people who kind of can understand the kind of constructions that I'm talking about, think of other applications and other interesting things to do with these constructions. Thank you.